Hello, thank you for tuning into this webcast on functional safety and automotive imaging with ON Semiconductor. This webcast will discuss the importance of focusing on automotive image sensing, examine functional safety in imaging subsystems, and describe the key metrics used when evaluating automotive image sensors. Just last year, data from the National Safety Council shows that 2016 was the deadliest year on American roads since 2007. With growing numbers of people texting while driving and performing other dangerous activities behind the wheel, at what point do automakers step in and assist the driver to protect drivers from themselves and the people around them? This is only perpetuated by the even more recent advances in autonomous driving. When human drivers are involved in accidents, even fatal accidents, news coverage is minimal. However, when autonomous vehicles are involved in even the most minor accidents, they typically make headlines even when the autonomous vehicle is not at fault. This is where image sensing is most needed and critical to consider in automotive applications. In virtually every autonomous vehicle, image sensors are the primary input in which these systems base their decisions. On the safety side, image sensors can be viewed as the eyes of the vehicle, and some ADAS systems only rely on image sensors in their processes. These eyes on the vehicles help us to see what we simply can't react to quick enough, and for that reason, automotive safety starts at the source with image sensing. For the purpose of describing an autonomous vehicle system, we will use this diagram to represent the key parts of the system, starting with the sensors as the inputs to the system, followed by the environmental mapping, which includes positioning the objects and their motion in the environment in 3 dimensions. The decision engine then takes the environmental map and makes decisions to affect the controls of the vehicle, resulting in changes to the control of the steering, braking, and other vehicle functions. In evaluating the functional safety analysis and detection methodology implemented in image sensors, we will consider the following key metrics used to achieve them. First, the sensor's ability to detect faults, the latency of detection or time required to detect the faults, the efficiency of the detection capability, and finally, the effect that these faults have on the rest of the system. Many image sensor manufacturers resort to educated guesses, engineering judgment, or standards-based guidelines as to the effectiveness of any given safety mechanism. Unfortunately, these methods have a very high margin of error due to the qualitative nature of these analysis methods. A more accurate method of analysis is through actual testing of these safety mechanisms through fault injection. Fault injection not only provides more accurate analysis, but also results in a much higher confidence in the results of the analysis. Many image sensors claim high diagnostic coverage, but place a significant computational burden on the processors in the system to perform extensive checking and analysis of test data and results. Unfortunately, there are many faults that cannot be detected at the system level regardless of the amount of computational resources available. That is, some faults can only be detected inside the image sensor circuits. Given the fact that in modern image sensors, anywhere from 50 to 75% of the total die area of an image sensor is occupied by analog circuitry, having an equally significant amount of analog safety mechanisms is critical to achieving high overall diagnostic coverage. Let's do an exercise. Do you see a fault in this image? To the naked eye, it's hard to tell. The truth is, there is a fault. There are in fact measurable differences in the pixel values. The point here is to show that not only are the effects of faults not often visible to the human eye, in many cases, these faults may not even be able to be detected by the system-level fault detection methods. It is entirely possible that certain faults that cannot be detected by system fault detection methods may in fact have adverse effects on image processing and recognition algorithms. This strengthens the case for having robust fault detection inside the image sensor itself. Beyond just the ability to detect faults is the latency, or time required to detect and report the fault to the system. In the timeline shown here, the time elapsed between the occurrence of the fault and when it is detected and reported to the system is defined as the detection time. The time that the system takes to react to the fault notification and to place the system into a safe state is defined as reaction time. For any system-level fault detection, the total detection time is T1 plus T2, whereas for sensor-based fault detection, the detection time is only T1. At 60 frames per second, this could be as little as 50 to 30 milliseconds. Regardless, sensor-based fault detection time is always much less than system-based fault detection of imager faults. Sensor-based fault detection gives the system the most reaction time possible. The need for real-time in-operation functional safety cannot be overstated. The image sensor is always imaging during normal operation, and having functional safety capability at all times is absolutely necessary. Any sensor that needs to be placed in a special state or needs to be taken offline in order to run certain safety mechanisms places the system in an unsafe state during that time. It is important to evaluate each safety mechanism with respect to its ability to operate in real time in all operating modes and without impacting the imaging operation. Implementing functional safety can have a significant impact on the efficiency of an autonomous vehicle system in terms of cost, performance, power, and development effort. Imaging sensors have thousands of potential failure modes, and implementing safety checks, whether performed partially or entirely in the system's CPU or GPU, can have a tremendous impact in CPU-GPU cycles consumed for this purpose. This may, in some cases, force the selection of more powerful CPU/GPU to offset the additional computational burden. Adding to that, the fact that some faults can be difficult or even impossible to detect outside the image sensor further reduces the efficiency of the system, as you can see from the fault here. A final consideration is the actual effect of a given fault. The exact effect of a given fault, for example a color shift, is very dependent on the specific implementation of image processing and object recognition algorithms. The only way to exactly determine the effect of a given fault is to have a faulted image processed by the algorithms and to analyze the results. This of course implies that there is a library of images for each fault. Such a fault image library can be used by algorithm developers to determine the effect of each fault on the system as a whole. This in turn can be used to modify the algorithms to be robust against the faults, and to potentially eliminate a number of those faults as safe faults, thereby increasing the diagnostic coverage of the system as a whole. So in review, detection is best done on the image sensor to ensure high diagnostic coverage. Latency is minimal when done on the sensor, leaving the most reaction time for the system. Efficiency is best when the sensor performs most or all data analysis on sensor, leaving the system to only monitor a fault/no fault flag. And to understand the effect on the system for every single fault, a fault image library provides a quantitative way to identify safe versus unsafe faults and to enable the system to achieve the maximum diagnostic coverage. With image sensors playing such a vital role in autonomous vehicles, functional safety on the sensor is the best way to provide the highest diagnostic coverage with the lowest impact on the system. ON Semiconductor's line of image sensors incorporate robust on-sensor safety mechanisms that help designers achieve high system diagnostic coverage while maximizing the available time for the system to react to hazardous events. They also enable the system to minimize the impact on cost, power, and computing resources while providing the highest level of functional safety. For more information on image sensors, please subscribe to our YouTube channel and visit www.onsemi.com. Thank you.